Today the topic which we are going to do is atoms. Essentially we will be talking about Bohr's model. Now according to Bohr's model, electrons revolve around the nucleus in stationary orbits. According to Bohr, the Rutherford model failed because the model that he proposed was unstable, but in Bohr's model the orbits are called stationary orbits and they are stable orbits. Now for any stationary orbit, the angular momentum is an integral multiple of h by 2 pi. So whenever you are discussing a stable orbit, the angular momentum will be an integral multiple of h by 2 pi. Now suppose you are talking about an atom which is either hydrogen or one electron species similar to hydrogen. Let the atomic number be Z. You know that the motion of an electron is due to centripetal force because it's a circular motion. The centripetal force is provided by the nuclear attraction. So you can write Z into E square by 4 pi epsilon naught r square equal to mv square by r. Now you have already got one relation between V and R, and now you have another relation between V and R. If you combine these two relations, this one and this one, then you will get V is equal to Z E square by 2n epsilon naught h, which can also be written as Z by n into E square by 2 epsilon naught h. And after putting the values of all the constants, it was found that we are getting 2.19 into 10 to the power 6 into Z by n meters per second. So if you are talking about, say for example, the ground state electron of hydrogen, then Z and n will both be 1. So the velocity will be 2.19 into 10 to the power 6 meter per second. Just like we combined these two equations to get the velocity, we can also combine these two equations to get the radius. So the radius will be epsilon naught h square n square by pi m into Z square. Now you can also write this as n square by z epsilon naught h square by pi m into E square. If you put the values of all the constants, you will find that it will come n square by z into 0.53 angstrom. So the radius of the nth orbit of a hydrogen-like atom with atomic number z is n square by z into 0.53 angstrom. So say for example we are discussing the ground state of hydrogen, so n and z will both be 1. In that case it will be 0.53 angstrom. Now the kinetic energy of an electron is half mv square, and we already have an expression for V. So after putting the value of V, we will get mz e to the power 4 by 8 epsilon naught square h square into n square. So this is the kinetic energy. The potential energy formula is this. So after putting the values, we will get mz square e to the power 4 by 4 epsilon naught square h square into n square. Now you will notice one thing, that if you take the kinetic energy as E, then the potential energy is minus 2E, and therefore the total energy is coming as minus E, that is minus mz e to the power 4 by 8 epsilon naught square h square n square, which can also be written like this. After putting the values, minus z by n square into 2.18 into 10 to the power minus 18 joules. So this is the expression for total energy. According to Bohr's model, the reason for emission spectrum of any atom is due to the fact that whenever there is a transition from a higher state to a lower state, then radiations are emitted. When an electron is making a transition from a higher state to a lower state, then there is release of radiations, and the energy of the radiation is given by hc by lambda, and that is equal to the difference of energy between the two states. So we can also write it like this. One by lambda is 2.18 into 10 to the power minus 18 by 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 into 1 by n1 square minus 1 by n2 square. So this brings us to the Rydberg's constant. This value which is written over here, it comes to 1.097 into 10 to the power 7. This is known as Rydberg's constant. So we are getting 1 by lambda is equal to Rydberg's constant into z square into 1 by n1 square minus 1 by n2 square. And 1 by lambda is also known as wave number. So this is the equation for finding the wave number due to a certain transition. So if you denote Rydberg's constant by R, in that case what we can do is that we can also write RHC minus RHC into Z square by N square is equal to the energy of the nth state. So if we denote Rydberg's constant by R, then RHC into Z square by N square will be equal to the energy of the nth state. So this is the explanation for the emission spectrum given by Bohr. In this emission spectrum, if N1 is 1, then the series of radiations is called the Lyman series and it consists of UV light. If N1 is 2, it is called the Balmer series and it consists of visible light. If N1 is 3, then it consists of infrared. It is known as the Paschen series. And similarly, if N1 is 4 or 5, then also we get infrared, and they are known as bracket and P-Fund series. So the series of emission spectrum lines corresponding to different values of N1 are designated as per this nomenclature. Now, you have already heard of the word ionization energy. So ionization energy is the energy required to ionize an atom. So for example, ionization energy of hydrogen in ground state is 13.6 electron volt. We can rephrase this in another way. The ionization potential of hydrogen in ground state is 13.6 volt. So either you can say ionization energy is 13.6 electron volt, or you can say ionization potential is 13.6 volt. Now there is a similar topic. Excitation energy. So excitation energy is the energy required to go from ground state to excited state. Excitation energy is the energy required to go from ground state to excited state. Like say for example, the excitation energy of hydrogen in first excited state is 10.2 electron volt, and the calculation for this is 13.6 minus 13.6 by 4. So the excitation energy of hydrogen in first excited state is 10.2 electron volt, or you could say the excitation potential of hydrogen in first excited state is 10.2 volt. The excitation potential of hydrogen in the first excited state is 10.2 volt. So these are the various details of Bohr's model. Now, you have already had a detailed look at Rutherford's model in lower classes. Now, Rutherford's model is used to estimate the size of the nucleus. Suppose this is the nucleus which the alpha particle is approaching. So let us say that the radius of the nucleus is r0. Let the atomic number of this nucleus be z. Now you are aware that the charge of alpha particle is positive twice the charge of electron. So Ze into 2e by 4 pi epsilon naught into r naught square is equal to the initial kinetic energy of the alpha particle. What happens is that when the alpha particle is approaching this nucleus, it has some kinetic energy, but as it approaches the nucleus, the repulsion of the nucleus, the work that is done to overcome the repulsion, it decreases the kinetic energy to 0, and therefore when the alpha particle is at a distance of r0 from the center of the nucleus, then the energy becomes completely potential. So the potential energy when it is at a distance of r0 is equal to the initial kinetic energy. So at this distance there is no kinetic energy anymore because repulsion has decreased the kinetic energy to 0. So the potential energy at this point is equal to the kinetic energy. So from here we get r0 square is Ze into 2e by 4 pi epsilon naught into k. So this is the formula which enables us to calculate the size of the nucleus. So that brings us to an end of this topic and also to an end of the chapter atoms.